The traditional RSA, we have three prime numbers, 3, 5, and 7. And we want to select basically a power D, which acts like the traditional RSA. It cancels out raising to the power of E. If you think about the proof of the traditional RSA method, you would see that the only key properties are that when you raise a number to the power of E and then raise it to the power of D, here E is the is a number which is part of the public key, and D is the number which is part of the private key. If you do that, then you get x to the power of ed, obviously. We want this number to be equal to x mod n, which is the same as saying that it should be equal to x mod any factor of n when n has different prime factors. Okay, so we know that in the traditional RSA, this condition is satisfied if ed is equal to 1. So I'm taking the powers of x on both sides. If ed is equal to 1 mod p minus 1 for any prime number which divides n, then we have this equality up there, mod p. So if this condition on the bottom is satisfied for every prime p which is a factor of n, then we have this. Now, to say that ed equals 1 mod p minus 1 for every prime factor p of n is the same as saying that ed minus 1 is divisible by p minus 1. This should be true for every prime number p which is a factor of n, right? So we want, in this case, we want ed minus 1 to be divisible by 2, which is 3 minus 1. We also want it to be divisible by 5 minus 1, which is 4. And we also want it to be divisible by 7 minus 1, which is 6. So for a number to be divisible by all of these numbers, you can either make it be divisible by the least common multiple of them, or you can choose the traditional method that the RSA uses, which is you can take ed minus 1 to be a multiple of the product of these numbers. So let's go with the easier method, which is we want to take ed minus 1 to be a product of 2 times 4 times 6. Okay, so I'm going to erase this part. ed minus 1 is going to be divisible by this number. What is 2 times 4 times 6? It's 48. So we want ed to be equal to 1 mod 48. Okay, so what is the e that we currently have here? Well, e is equal to 5, right? So we have to find the multiplicative inverse of 5 mod 48. Okay, in order to do that, we can either follow the extended Euclid's algorithm, or we can try a few guesses. I'm gonna follow a trick, basically. So we want 5d to be equal to 1 mod 48, which means that 5d minus 1 is going to be divisible by 48. Now if you notice, we can always take d to be a number which is less than 48, right? if d is less than 48, then 5d is less than 5 times 48, right? So this whole number is a multiple of 48, which is less than 5 times 48. So it can be either 0 times 48, 1 times 48, 2 times 48, 3 times 48, or 4 times 48. Okay, let's try these and see which one works. Well, this case doesn't work. Why? Because 5d minus 1 can never be 0, because 5d minus 1 is always minus 1 mod 5. Okay, so this case is a no. Okay, what about 1 times 48? Well, if 5d minus 1 was 48, then 5d would have been 49. But 49 is not divisible by 5, so this case is out too. How about 2 times 48? Well, in that case, 2 times 48 is equal to 96, right? In that case, 5d should be equal to 96 plus 1, which is 97, which is not divisible by 5, so this case is out too. How about 3 times 48? Well, 3 times 48 is equal to, okay, let's do the multiplication. It's equal to 144. Okay, so this case is the one that works. 5d minus 1, if it is equal to 144, then 5d is equal to 145. Okay, this means that d is 145 divided by 5, which gives us 29. So the answer is going to be d equals 29.